Thank you, and good evening, everyone. My thanks go to the organizers for letting me give this talk and to you for joining me as I speak to you about inertia in the unconscious brain. So my group focuses on studying anesthesia and its implications for studying consciousness. Most of us believe that states of deep anesthesia are unconscious. So in anesthesia, we have a tool for reversible unconsciousness, if you will. Whatever consciousness is, it should disappear as anesthesia is induced and reappear as we emerge from it, as Andreas' talk just gave us exciting examples of. But now, one of the strange results that anesthesia has contributed to the science of consciousness is that neural inertia may be present in the brain. That is, losing and gaining consciousness may not be symmetrical processes, they may be fundamentally different, which has implications for the philosopher as well as for the clinic. And a version of this has been long known to anaesthetists. It's commonly observed that the anaesthetic dose required to make a patient lose consciousness is normally higher, as we see on this red curve, than that at which they regain responsiveness. But it's worth noting that the key changes happen in the brain, and they don't have to track with behavior. You can imagine a horror scenario where a patient is unresponsive yet fully conscious during a surgery, which we clearly want to avoid. So for understanding the loss of consciousness, we have to look at the brain and not just the behavior. And our group does this using a variety of modalities, such as fMRI. But today I want to focus on the electrical activity on the brain, that is the electroencephalogram or EEG, and how we can look at consciousness inertia in there that we observe. So let's briefly look at the EEG signatures of anesthesia. So EEG, just for completeness, is measuring scalp electrical potentials. Here's an example of me with shorter hair from pre-COVID, having some EEG done. And during the awake rhythm, if you looked at the activity from one of these electrodes, you'd see quite low amplitudes, fairly high frequency activity, lots of alpha around 10 hertz, gamma around 40 hertz, and stuff like that. But when you go into deep anesthesia, large changes happen in the kinds of brain signals that we observe. More specifically, you get the appearance of what we call slow waves, which are these kind of large waves around 1 hertz, where large, broad cortical areas alternate between up states of high activity and down states of relative silence. And these kinds of slow waves are also seen in deep NREM sleep and in disorders of consciousness. So again, it seems to be a kind of one of the natural unconscious rhythms of the brain, which we'll talk about a bit later. But for completeness, if you keep increasing the anesthetic dose even further, eventually you start losing these slow waves and you go into this kind of a pathological state, which we call burst suppression, where you alternate between these kinds of bursts of high frequency activity and relative silence. So that's enough about EEG during anesthesia. We see that slow waves are important, but one of the reasons why that's exciting is an effect that my supervisor discovers, which is called slow wave activity saturation. So I mentioned to you that these slow waves start increasing and appearing as you start increasing the anesthetic dose. But moreover, this does not happen forever. And at a certain anesthetic dose, this activity saturates, and so you don't get more slow waves past that. And in fact, our group has been able to show, for example, using concurrent fMRI imaging, that you see important changes in how the brain processes information, such as laser and auditory stimuli, as well as important connectivity changes, for example, in the thalamocortical system. So it seems that this point, SWAS, or slow wave activity saturation, is important for potentially measuring individualized loss of perception, if not consciousness. And so you can also see this here on this spectrogram, where you can see this, all of this low frequency activity at the bottom, as well as some alpha and theta activity. But it's not that simple, right? It would be nice to have this kind of, slow wave saturation. Basically, that's our mark of unconsciousness. But I've just mentioned to you that we seem to see inertia, right? This curve would look different or if a person was waking up rather than losing consciousness. And at very high doses, we see this slow wave activity break down, right? You don't see this plateau last. So we need to do a little bit more work. And to do that, let me introduce you very briefly to the idea of hysteresis, where basically a system is hysteretic if its current state depends on its history. And to give you a trivial example, if you have a regular paperclip, if you put it next to other paper clips, nothing happens. But if you were to rub it on a magnet, for example, and then even after you remove the magnet, that paperclip will remain magnetic. And therefore, the state of the paperclip, is it magnetic or not, and which way is its north pole, is dependent on its history. And to get a little bit more precise about this, we can start drawing hysteretic curves like this one, where on the x-axis we'd have the kind of external field that we're applying, and on the y-axis we'd get the field of the paperclip. And you can see that the curve of when we try to magnetize it and then demagnetize it is not the same. That's what we mean by hysteresis or inertia in the system. It's kind of area between the forward and reverse curve. And we can start to see how this is useful as applied to the kinds of inertia that we see in consciousness, and particularly in anesthesia. So it does seem that we have evidence for the brain being kind of stuck in a state. For example, when we look at slow wave power against anesthetic dose, we've seen that as we lose consciousness, you have this kind of nice sigmoid response. But on regaining consciousness, the curve is normally different. And you, for example, regain consciousness at a lower concentration, and you may have lost some of that slow wave power at those high doses. And if you like to think of this in terms of an energy landscape, there's plenty of consciousness ideas related to that. You can imagine that just an awake brain has the lowest energy state, which is conscious. And as you increase the anesthetic concentration, you shift that energy landscape to where at high doses it's the unconscious state, which is now the more energetically favorable. And moreover, it's sticky in a way, where you can see that you need extra energy to kick back to the conscious state. And so we've got this hysteresis present, but there are very few kind of explicitly hysteretic models in the literature that can help us make sense of this and help us model these effects. And so I want to introduce you to a very simple way that hysteresis is modeled in physics, in physical processes, and how I modify that to have this apply to what we see in anesthesia. So we start with a fundamental unit, which is an individual hysteron. And this is simply in the magnet, this could be, a small part, a couple of millimeters cubed of your magnetic material. In the brain, this could be, tens of thousands of neurons, part of the cortical column. And we give it two states. So for example, for the magnet, this may be north pole pointing up or down. And we can see that we build hysteresis into it. That is, as we start changing the external parameter, so for example, the external magnetic field, we can see that the flipping from 0 to 1 happens at beta if we go from the left. But if we were starting in state 1 and flipping to state 0, that only happens at a threshold alpha. And once we've got this fundamental unit, we can combine many of them and have the summed activity. And it turns out that this gives rise to collective hysteretic behavior, which explains the kinds of curves that we've seen before. So let's see how we can apply this to our model of slow wave power, which seems to be important in consciousness, in particular as it applies to anesthesia. So we've seen that we're interested in fitting these slow wave activity curves, both clinically and from a kind of more consciousness science point of view. But the current models, for looking at through sigmoids and things like that, clearly not sufficient because we have neural inertia, as well as this loss of slow wave power at high concentrations. So just to flesh this out a little bit more, this is quite a nice, clear analogy between, borrowing a concept from physics and applying it in consciousness studies. So basically, the state is, for example, the brain producing slow wave power and your lump of iron being more and more magnetic. The kind of changing variable is, on one hand, we're changing the anesthetic concentration, which is driving more and more slow wave power. And on the other hand, we are changing the external field, which is driving more and more of this internal magnetization. And finally, to make the analogy complete, we see that at very high anesthetic doses, we start losing slow wave power, which you could see as, for example, heating the magnet at high fields, because that kind of destroys magnetization and randomizes all the individual magnetic dipoles. So again, to make this a little bit more mathematical, we start with the Preisach model that I already outlined with the alpha and beta thresholds, but we introduce a third threshold, gamma, at high doses at which the slow wave power is lost. And again, we have many of these individual hysterons, individual building blocks, and these thresholds have a distribution, which is called a Preisach plane. And once we do that, we obtain a model which is now very flexible and is able to model inertia as well as the breakdown of slow wave power at high concentrations. And in fact, the model is really flexible, depending on kind of how exactly the parameters are set up. You can not even approach the high concentration breakdown, and you just have kind of what I call stable SWAS. At deep anesthesia, maybe you've lost a little bit of slow wave power. I've seen that before. Whereas at burst suppression, you may have lost most of your slow wave power. And you can even model reverse hysteresis where the induction is at lower doses than the emergence, if that were to happen. So it's a very flexible model. Here's an example of kind of a visual representation of it. You can see these individual hysterons. And as you start increasing the anesthetic concentration, more and more of them start flipping into the slow wave producing state until at high doses they start losing it again. And we have validated this in real data, where in 21 pre-surgery anesthetic patients, we've seen that we have their frontal EEG, and the model that we developed, the Hysteron model, fits the data significantly better than the previous kind of attempts trying to look at it in terms of sigmoid. You can see that here, for example. And when you look at on the group level, the error between predicted and observed is significantly smaller, and moreover, the model is unbiased. So it seems to really be valid for the kinds of things we see in the clinic. But the final kind of little spanner in the works I want to talk about is that one of the reasons why anesthetists haven't been kind of more active in the consciousness community banging this inertia drum is that it used to be thought that a lot of it is just due to system delays, because the concentration that you observe, for example, the anesthetic that you give them or kind of as they're breathing it out, is not the same as the concentration at the effect site, which is the brain in this case. You can see that here, for example, if we were to give them the red dose, what may be happening in the brain is actually with a slight delay, kind of a simple first order differential equation, which is the blue curve. And this has the potential to shift your hysteretic appearance. I'm giving an example of that here, where you can see that depending on what we believe the concentration is at the effect site, the curve can change quite a lot. But a couple of things to say here is that, first of all, some hysteresis is inevitable. You may kind of shift the appearance from, say, the high concentration decrease to this kind of, for example, parallel shift between induction and emergence, but it's quite difficult to actually get rid of all of the hysteresis. And moreover, the model that we developed can take into account all of these curves. So irrespective of pharmacokinetics, we are able to fit this kind of inertial and hysteretic dynamics. So to kind of start to draw this all together, we've seen that inertia or hysteresis seems to be present in consciousness, especially as when it's lost in anesthesia. And we've seen how slow waves are important in anesthesia, and we get this phenomenon known as slow wave saturation. And by drawing an analogy, borrowing concepts about hysteresis from physics, we were able to develop a Hysteron model, which can take into account all of the things that we actually observe when we go and look what's going on in the brain. And you can see why this would be interesting, for example, in the clinic, because you can start to categorize patients based on, did they lose their slow wave plateau? Does that have an impact on kind of their post-operative recovery? How sensitive are they to hysteresis? You can make all these statements with this model that can finally fit your hysteresis. And I want to also, thank you. And I want to speak a little bit to kind of what the basis of hysteresis may be, to kind of know kind of where it's all coming from. And already on the molecular level, we see some hysteresis. We've seen the magnet, right? Individual kind of iron molecules or atoms may show hysteresis. But there is some modeling evidence to suggest that on the cellular level in the brain, individual neurons may also show hysteresis as anesthetics are applied. That's what I'm showing here. And then the idea would be that that kind of permeates to the network level, where whether you actually have consciousness or not in the brain, and how that dynamics tracks becomes sticky and shows inertia or hysteresis as well. And to finalize, we believe that this may have links to other branches of consciousness science. You can imagine that certain altered states, for example, in psychedelics, could show neural inertia as well. Sleep seems to. If you've ever woken up from a nap, not being able to kind of continuing with your day, you've experienced sleep inertia. And it may happen in disorders of consciousness as well. If you are, for example, in coma, it may be more difficult for you to return to a state of consciousness. More to the model, one kind of fairly obvious extension is to make a coupled model, because if one region is producing slow waves, it's more likely that regions near mine might be. And you can see how this can give rise to kind of interesting metastable dynamical behavior. But for example, if we introduce one hysteron, which is producing slow waves, and some coupling, we can get waves emerging in the system, which is what we observe in real life. The slow waves are actually traveling waves. So I hope you found that interesting. I'd like to thank all of my colleagues from Oxford, the physics department, FIMRID, and to all of you for paying attention. And I welcome any and all questions you may have.